All right, ladies and gentlemen, in this lesson, we are working on our integration techniques. And this is the quiz assignment. At this point, you've solved integrals by just kind of anti-differentiating. You solve integrals by rewriting them. And you've solved integrals by substitution. The question that I want you to focus on in this assignment is this question here. When do we use u substitution and when do we try to rewrite the integral? Okay, so this is the first time you've had to choose between these two things. In the past, I've given you all u substitution problems or all sort of rewrite the integral type problems. Here you have to decide which is which. So we'll talk about that question as we go. As always, in this particular video, feel free to skip around to just the questions you need. But if you're stuck on a particular problem, my guess is it's going to be related to this question here. Okay. Now, all that being said, our first problem is actually just a very basic integration problem. So if we look at a derivative sheet, we see that the derivative of tangent is secant squared. Okay, so that means the antiderivative, or an antiderivative, because there are many antiderivatives of a particular function, right, would be 3 tangent of x. That would get us 3 secant squared when we take a derivative, plus 2x. Okay, and let's see if we can find that answer choice. Yeah, that is B, right? And notice they could have given us any constant too. So for example, 3 tangent x plus 2x plus 5 is also an antiderivative of this particular function because the 5 has a derivative of 0. Here, for this particular choice, my constant is 0. But plus 5 would be also a correct answer. 3 tangent x plus 2x plus 1 million will also be a correct answer, and so on. They would never give you more than 1, but just something to keep in mind. Okay, number 2 now is where we return to this kind of guided question for this assignment. So here, this is a great example. We have a function within a function that we're integrating. So it might be tempting to say, let u equal x squared plus 1, and then I could rewrite this as u squared. Du, though, well, let's take a look, is 2x dx, right, is the derivative of this. Notice that x term doesn't show up. So if we say the integral of u squared dx, there's no way we can substitute in du because we don't have an x to make du, right? So this will not work because there's no derivative of u that shows up in our function. So that means the only way we can solve this one is by rewriting it. So I'm going to square this. I'm going to get x to the 4th plus 2x squared, and I'm just using the FOIL method or the Punnett square method, plus 1 dx. Okay, so I've rewritten this, and now I'm going to integrate. So this is just a power rule problem. I get x to the 5th over 5, plus, you can see which choice it's going to be already, right? Plus 2 x to the 3rd over 3, right? Because I added 1 and then divided by the resulting power, plus x plus c. Okay. So if this one had an x outside the parentheses, I'd want to use a u substitution, but it did not, so I have to rewrite it to use one of my derivatives rules. Okay, so the answer to this question is we use u substitution when we can find a du in the integrand here. If we can't find that du, we have to try some other strategy. This one is simply about rewriting the question. Okay, so this is a question that tests essentially, do you know to change the bounds of integration, and do you know how u substitution works? Okay, so let's start by finding du. So du is going to be, well, the derivative of x to the 1/2, this is, right? So I get x to the negative 1/2 times 1/2 dx. Okay, so I have to substitute that in. Notice, maybe I should rewrite this here to make it clear. Notice that this integral is equal to the integral of 1 to 4, from 1 to 4 of e to the square root of x times square root of x on the bottom is the same as x to the negative 1/2 dx. Right, so there is my dx piece, right? So I have this and this, which should make me happy. And then I want to sort of isolate this, so I'm going to say times 2 du to cancel out my 1/2 x to the negative 1/2 dx. Okay, so I've manipulated that a little bit. I'm going to make my substitution now. So my integral is going to be equal to the integral. I'm going to skip the bounds for a second because remember I have to rewrite those too. But it's going to be e to the u times 2 du. E to the u is my top, and then du is this x to the negative 1/2 dx. And notice we can now eliminate d and e because they're missing that 2. My bounds, well, u is square root of x, so my bounds are going to be the square root of each of these, square root of 4, square root of 1, which is just 1 to 2e to the u du. Okay. And we don't actually have to solve it, although we could at this point. This is a pretty easy integral to solve. So that is choice C. Okay, so notice my du shows up in the integrand, so I can use u substitution here. Next one. So here's a problem where we might be tempted to use a u substitution. So you might want to say let u equal x squared, and then du would be 2x dx, right? And that seems like at first glance like it might work because we have an x on top and u on the bottom. So we have u and then some kind of du up top maybe. If you tried that, you probably ran into issues. And here's why. So this dx, we usually just kind of ignore it. It's just part of the notation to us, right? But this is a multiplicative relationship. So dx times x, 4 times dx. So if I rewrote that, I would get this integral. X dx minus 4 dx over x squared. And usually we do not do that, so I just distribute it, right? Usually we do not do that because it doesn't help us solve the integral. But that's really what this means. And notice now, I have x dx in my first term, which works for my substitution, but I have no x in that second term, so I could not turn this into some multiple of du. So that's not going to work, right? By the way, the reason we multiplied, this gets back to our Riemann sum idea. This is really the base of a rectangle. This is really the height of each rectangle. And now when we integrate, we're talking about infinitely small rectangles, right? So if I drew this picture, I have some curvy function. That function is x minus 4 over x squared. And then, so that would be the height of my rectangle. Base of my rectangle is dx, or vice versa, right? But that's why it's a multiplication relationship, right? So base times height is really the function times the change in x. That was kind of a digression, however. Let's go back to solving this integral. So u substitution isn't going to work, and will never work when we have something being added or subtracted to the derivative of the u we might pick. So instead, we're going to rewrite this. So I'm going to say this is the integral from 1 to 2. I'm going to split up my fraction, x over x squared minus 4 over x squared dx. And then it becomes a sort of easier power rule integral written this way, right? So this is the integral of 1 over x minus 4x to the negative 2 dx. So I've just rewritten it again using my exponents rules. The derivative, remember, of natural log, this is why there are natural logs in the answer choices, is 1 over x. So the antiderivative of 1 over x is natural log of x. Here, we're going to add 1 to the exponent. Oops, that gets us -1. And then we're going to multiply times the reciprocal, right? So here, we're just going to get a +4, right? And then we can check, is the derivative of 4x to the -1 power -4x to the -2? And it is, right? So subtracting 1 from the power gets us -2, and multiplying times that -1 gets -4. So this is the correct integral. We're going to evaluate that from 1 to 2. Those are our limits of integration. That gives us ln of 2, natural log of 2, plus 4 times 2 to the -2. Oh, -1 I meant to say. So I plugged in 2. Now I'm going to do minus, and I'm going to plug in 1. Natural log of 1 plus 4 times 1 to the -1. Okay, easy enough. Then I'm just going to simplify, so natural log of 2. This becomes 4 over a +2, so plus 2. Natural log of 1 is just 0, because anything to the 0 power is 1. And then I have minus, and then 4 over 1, so minus 4. So this ends up being natural log of 2 minus 2, which is choice B. Okay. If you didn't follow this explanation of why we can't use the u substitution, that's okay at this point in your calculus career. But you should understand how I rewrote this and how I solved the integral. Okay, here's a spicy one. So the derivative of y is tangent. Then y equals one of these things. So there's a couple different ways you can go about this. The first thing you should do is look at your derivatives rules. So what I'd be looking for, right, is tangent of x in one of these on the right hand part of the equality, right? So I'm looking for the derivative of some function being equal to tangent of x. And we don't have one, right? So there's a couple different ways we would want to tackle this. The easiest way, and the way that I want you to focus on at this point in your calc career, is just take a derivative. Take the derivative of each thing and see which one gets you tangent of x. This has to do with the fact that dy dx, like tangent of x, is equal to sine over cosine, because that's the definition of tangent, or a definition of tangent. And you learn that when solving problems using the unit circle. But let's see what we get when we take the derivative of all these. Let's see if we can't figure it out. So I'm going to look for derivative of secant, or we'll start with tangent. So the derivative of tangent is secant squared of x. So this would get us, so I would do power rule first, 24 tangent of x times the derivative of tangent of x, which is secant squared of x. Derivative of c is 0. And this doesn't seem to get us close, right? We'll come back to that one if we need to, but this seems to be like not even close to tangent of x to me. Secant squared of x, so we'll do 2 secant of x, and then chain rule times the derivative of secant, which is secant x tangent x. And now they start to really get crazy. So natural log 1 over secant of x times the derivative of secant x, which is secant x tangent x. Interesting. So look what happens here. We're multiplying. Secant over secant is just 1, right? What's left over is tangent x. So that is our solution there. Okay? So this is kind of illustrates why integrals can be harder than derivatives. So taking this derivative was fairly easy, but then when we simplified, we got this interesting result, right? So it's not entirely clear that the integral of tangent x is the natural log of secant x, but that's what we get in this case. Then we can continue to check the rest of these. So this one, you get 1 over cosine of x, and then the derivative of cosine is negative sine of x. So by chain rule, this is really close, right? Negative sine of x over cosine of x. So this has the wrong sign. This would be equal to tangent x, but negative tangent of x. And the last one, we could check. We'd have to do product rule. We've already found the correct answer, so we'll skip it. So this is just an illustration of like a good test-taking strategy, is sometimes just taking the derivative of your answer choices is a good move on multiple choice questions. All right, we have 2 more, and these are my particle motion problems. So to tackle these, we will remember the relationship between position, velocity, and acceleration, which is this, right? So taking the derivative of position gives us velocity. Taking the derivative of velocity gives us acceleration. And then the opposite is also true, so taking the integral of acceleration gives us velocity, and taking the integral of velocity gives us position, right? So this means that velocity is the rate of change of position, and the sum total of all the changes in position gives us position, right? So the sum total of velocity gives us position. Okay, so you need to decide, based on what is given to you, whether you need to integrate or differentiate. In this case, we're given velocity. We want position. So that means I have to take the integral of the function that is given to me. So I have 1 minus sine 2 pi t dt. And what I'm going to do to make this a little bit easier, this is a somewhat spicy integral. I'm going to split it up. So I'm going to say the integral of 1 dt plus the integral of negative sine 2 pi t dt. Okay? First integral is easy. We're going to start with the harder one. So there's a couple different ways I can think about this. I could think of either reverse chain rule, or I could actually even do a u substitution. So I'll show you that second way with a u substitution because I think it's actually easier than trying to think like the reciprocal of 2 pi and all that. We're going to get the same result no matter how we do it. So I'm going to let u equal 2 pi t, and then du is going to be just 2 pi dt. Okay, so that means that dt is equal to 1 over 2 pi du. And this should make us happy, right? Because this is just a constant, just a plain old number. So that means that constant function shows up in our integral, right? We can make this substitution. So when I do that, so first of all, the integral of 1 is just t plus c, right? But we'll write the plus c at the end when we've integrated everything. And then I get the integral of negative sine. I'm going to leave a space here for me to write my constant here. Negative sine of u, so I've plugged in u now, du. But what I'm plugging in here is dt is equal to this, right? So du and then 1 over 2 pi is my dt. Okay, so now I integrate that. The derivative of cosine is negative sine. That means the antiderivative of my negative sine is cosine. So this really becomes t plus 1 over 2 pi cosine of u plus c. And then I'll plug my u back in. So my u is 2 pi t. So my result is t plus 1 over 2 pi cosine of 2 pi t plus c. And now, what were we looking for again? We want the position function. We're given this initial condition. So this is, remember, called an initial condition. We're going to plug this in to figure out what c is. So we're going to say 0 equals 0 plus 1 over 2 pi cosine of 0 plus c. And this is easier than it looks. Actually, I'll come down here. So cosine of 0 is 1, right? So I get 0 equals 1 over 2 pi times 1 plus c. Well, that means c equals negative 1 over 2 pi. So my position function x of t is equal to this result with c equal to negative 1 over 2 pi. So t plus 1 over 2 pi cosine 2 pi t minus 1 over 2 pi. Put some parentheses around some of these things for good measure. And that's my position function. This is about as spicy as these problems can get on the no calculator section of the AP exam. So this is like the hardest integral you might have to solve by hand, I think, and we just did it. We do have one more question left, so this was the solution to number 6. Number 7, thankfully, mercifully, is a lot shorter. The acceleration of the particle. Well, we have velocity. Acceleration is just the derivative here. So this is just actually a derivatives question. So the derivative of 1 is 0. We have a minus. The derivative of sine is cosine. 2 pi t. And then chain rule, right? So times 2 pi. So that's a of t. Much easier than integrating in this case.